Hi all, so this presentation focuses on bipartite networks and how they can be modeled using ERGMs. So as Jim mentioned, bipartite networks or two-mode networks are networks in which there is some partition of the nodes into classes where connections can only be made between classes and not within classes. So a common example of a bipartite network is the Southern Women data set that Jim alluded to, which contains information on events that women in a Southern town attend. So the name of the data set is Davis, and it exists as part of the latent net package, which also depends on the ERGM and the network packages. So we're not really focused here on using the capabilities of latent net, we're mainly just using it for the data set. So when we type the name of the data set here, we see that the network has 32 vertices, and 18 of them over here are mode 1 nodes, which means 14 of them are mode 2 nodes. In this case, the 18 mode 1 nodes represents the women, and the 14 mode 2 nodes represents the events. So we can view a plot of the network using the plot function. We can also use the plot.network function. So in this plot specifically, the red circular nodes represent women, and the green diamond-shaped nodes represent events. So it's not very obvious from this plot, but edges only exist here between the red nodes and the green nodes and not within them. So as Jim mentioned, the adjacency matrices for bipartite networks are rectangular, with the rows typically representing people and the columns typically representing groups. So to get the adjacency matrix for the Southern Women data set, we can use the function as.matrix.network adjacency here. And as we can see here, each row represents one of the women and each column represents one of the events. So a 1 in this case indicates that the woman in that row attended one of the events in that column. So now if we can consider affiliation networks as hypernetworks. So hypernetworks are networks in which an edge might not need to consist of 2 nodes. So in a hypernetwork, an edge might get to say for every node whether it's in or whether it's out. So if we consider a hypernetwork now in the context of the Southern Women network, we can consider the Southern women as nodes and the edges as arbitrary subsets of those women. So it's essentially the same thing as saying that we're going to link up each woman or each woman with an event that she attended. So now the edges get paired up with events in the bipartite setting. So knowing that we can express hypernetworks as bipartite networks then allows us to analyze hypernetworks using tools that we would use for bipartite networks. And now looking at some of those tools for bipartite networks. So here we fit the Southern Women data set to the Erdos-Renyi-Gilbert model. So in the Erdos-Renyi-Gilbert model, each possible edge appears independently and with equal probability. So we fit the model in ERGM using the edges term here, and the estimate over here gives us the log odds of a tie forming. And we can also estimate this directly. So given 252 possible edges here, and with 89 actual edges in the network, the estimate is given by the log of 89 over the 252 minus 89. And here we get the same estimate as we did when we ran the ERGM. So now we can consider the following model that uses the dyad independent term, sociality. So a dyad independent statistic is a statistic such that if a single edge in a dyad is toggled to be on, so if it's toggled from 0 to 1, then the change in the statistic can be calculated without knowledge of the other dyads in the network. So the sociality term specifically is a term that adds a separate statistic to the model for each node equal to its degree. So we can use this summary function here to return the observed statistics for the network. And here we're considering sociality on the women nodes. So we have 18 terms that get returned. And the 8 over here, for example, represents that the first woman, Evelyn, attended 8 events. So it's important to note that when an ERGM consists only of these dyad-independent statistics, the model can be fit using logistic regression. So while this does become more efficient computationally, it's often rare to find a social network model that includes only dyad-independent statistics. So looking back at the dyad-independent model with the sociality terms, we can calculate the coefficient estimates by hand as well. So over here, we have the ERGM-based estimates, fitting in ERGM and R. And if we consider node 1 here, note that each of the woman nodes can have a max degree of 14, given that there are 14 events. So if we consider node 1 over here, again, we noted that it had a degree value of 8 when we use the summary command. So the coefficient estimate is then equal to the log odds of 8 over 14, which is equal to the 0.2877 here. So analyses from one-mode networks are often applied to bipartite networks using projections. So projections essentially allow us to see the shared groups among people or the common membership among groups. So every bipartite network gives rise to 2 separate one-mode projections. The first is a person-to-person projection, and the second is a group-to-group projection. So an edge between 2 nodes exists in the one-mode projection if and only if there is at least one two-path between the 2 nodes in the original bipartite network. And what this means is that if the person-to-person projection, an edge exists between 2 people if they are both a member of at least one group. And in the group-to-group projection, an edge exists between 2 groups if they have at least one common member. So we can calculate these one-mode projections using the adjacency matrix for the bipartite network. So if we let A be our adjacency matrix with dimensions P by G, where P is the number of people and G is the number of groups, then the calculations are given as follows. So the person-to-person one-mode projection is given by A times A transpose, which is a P by P matrix, and the group-to-group one-mode projection is given by A transpose times A, which is a G by G matrix. So if we consider it now with the Southern Women data set, if we look at the woman-to-woman one-mode projection, we can again do the matrix multiplication here with the adjacency matrix. And over here, this network contains 18 nodes. Each node is one of the women, where an edge exists if the 2 women were in at least one event together. And now we can also consider it for the event-to-event one-mode projection. So here, this network contains 14 nodes. Each node is one of the events, where an edge exists if the 2 events had at least one common woman who attended both. So one of the downsides to modeling using the one-mode projection is that the information contained in the bipartite structure may be lost. So this is because when we use the one-mode projection, we're essentially modeling the generated data instead of modeling the data generating process. So a key point in which this is visible is that different bipartite networks can produce the same one-mode projection. So in order to ameliorate this loss of information, one method we can use is a weighted one-mode projection. So an example of a weight that can be used is the specific number of 2 paths that exist between the 2 nodes in the original bipartite network. So considering it specifically in the context of the Southern Women data set, if we're looking at a weighted woman-to-woman one-mode projection now, again, we have a network consisting of 18 nodes for each woman, but now each edge is weighted by the number of events that the two women have both attended. And we can use the apply function here to retrieve the weights from the woman-to-woman projection matrix that we generated. So we can consider the same thing for the event-to-event one-mode projection. Again, this network contains 14 nodes where each node is one of the 14 events, and each edge is weighted by the number of women that have attended both events. So while the weighted projections do help retain some of the information that's contained in the bipartite structure, they are not without drawbacks of their own. So one of them being that they're often more difficult to analyze using ERGMs. Another is that they do lose some information. So for example, if we consider the Southern Women Network, an example of the information that they may lose is how many events a group of women larger than 2 attended together. Another thing that we might not be able to tell is which events they attended together. So the key idea here is that modeling using one-mode projections is often not ideal unless the lost information is not needed in the analysis.
As some examples of the kinds of information Alina might be referring to that could be lost from projection, let's consider a few statistics that would be dyadic dependent terms in an ERGM. There's a figure here that consists of a subnetwork generated from the Southern Women Network. And we see in the upper left what's called a 3-star. And the 3 red dots are women. They all attended the same event, which looks like E10 in this case. Then on the right, on the upper right-hand corner, there's a 4-cycle. A 4-cycle consists of a pair of women and a pair of events. And both women attended both events. At the bottom, there is a 2-star, and a 2-star consists in this case of 2 women who attended the same event. We could also imagine that stars would be centered at the women, so you could think of a single woman who attended more than one event. And all of these structures can be defined in the ERGM package. You see here a summary function applied to the Davis network. Here we have B2 star of 3. That's a 3-star centered at the second mode of a bipartite network. B2 refers to bipartite second mode. And so this will be a 3-star centered at an event. And if you count up all of the 3 stars centered at events, you find that there are 878 in this particular network. The 3 stars and 4 cycles are examples of statistics that cannot be reconstructed from a projection. On the other hand, the 2 stars can be, and it's demonstrated at the bottom of this slide that you can in fact use the weighted projection matrices that Alina calculated earlier to obtain those 2-star counts. And again, these statistics, these 3 stars, 2 stars, 4 cycles, they all now destroy this dyadic independence property that Alina referred to earlier, and later we'll see that that has some implications in terms of how we can model these networks using ERGMs. What we're looking at right now is a model that contains, well, 2 terms according to the specification in ERGM. There's sociality with all 18 nodes, and then there's a 3-star term centered at the B2 nodes. And because that 3-star term is dyad dependent, that means the entire model is dyad dependent, which means that we can't fit this model using simple logistic regression the way we can when all of the terms are dyad independent. So that proves problematic for a number of reasons that we don't have nearly enough time to go into right now. but it means that the estimates that you're looking at are actually obtained via an approximate algorithm. So there's a little bit of stochasticity involved, some randomness, and so these coefficients will be slightly different if you were to rerun the fitting algorithm. If you look at the bottom here, this is you'll notice that I've cut off most of the sociality coefficient estimates, and down here at the bottom we see the 3-star coefficient estimate, which is positive, and it's highly statistically, it's highly statistically significant with a p-value of 10 to the minus 11th. What this tells us is that in this particular network, we see more of these 3-woman groups who attended a single event than we would expect by chance alone, even if we correct for each individual woman's propensity to attend events overall. Let's look at a different affiliation network now. This one is much larger. It's due to Dan McFarland, and you'll see in the next few slides just some data cleaning activity. And for those of you who have dealt with real data sets, you know that cleaning data is often something that's overlooked in an introductory statistics class where you're magically presented these data sets that are nice looking and there are no problems. So the next few slides just load a text data set, clean it, and put it into the format necessary to be used in the ERGM package. But what you see here is that there are some students in grades 7 through 12, and you'll notice that these students belong to certain clubs. And so the affiliation network has 2 modes of node. One mode is the students, and the other mode is the clubs. And for instance, you can see down here, you can see down here that this student, whose ID is 101496, has not joined the Asian club, the Hispanic club. Maybe the student joined no clubs at all. There are 91 possible clubs that the student could have joined. And cleaning data, getting rid of missing values, turning this now into a network object in R, and adding some nodal covariates. That's what you see with the %v% operator. And at the end, what we get is a single object called school network in this setting. And school network has, as you can see, 1,363 nodes. And it has a value bipartite of 1262. So that tells you that there are 2 modes in this network, 1,262 of the first type, and the remaining, in this case, 1,353 minus 1262 will be the second mode. We also see the attributes, or the vertex attributes that we have recorded on this network data set. This is a depiction of the network data set. It's a little bit busy because there are so many students, but you get an idea for the bipartite nature if we are able to separate the nodes into these 2 stripes, one on the left and one on the right. And you can do all sorts of things like this using the plot.network function here. So let's look at a simple ERGM, ERGM fitted in the ERGM package to the school network data set. In this case, we're simply looking at B1 factor gender and B1 cov grade. So we're looking at covariates that are measured on the nodes, gender being one of them, grade being another. And this particular network model has only 3 terms, edges, and then these 2 main effects of gender and grade. You'll notice that we're treating grade in this model as a quantitative variable, even though we could instead treat it like a categorical variable, thinking that 7th graders is one category, 8th graders is another category. But in this setting, what we're doing is we're treating the number 7, 8, 9, 10, 11, 12 as just a number. And so this coefficient would go in front of that number, just as it would in a regular linear regression. This is a simple model to fit. It can be done using logistic regression. And because of that, it will get the same answer every time we fit this model using the ERGM package. One other small note here that's cosmetic is that instead of using node factor, which we would normally use in a single mode network, we're using B1 factor. In fact, there's nothing wrong with using node factor. However, in our example, our vertex attributes sometimes have missing data. And that's not because the data aren't cleaned. It's because when we're talking about students versus clubs, some of the attributes have no meaning in one or the other. In this case, there's no such thing as the grade level of a club. And so if we tried to use node factor of gender or node factor of grade, because clubs have neither of those, we would actually get an error from ERGM. The B1 factor and B1 cove terms then just make this a cleaner way of specifying, yes, we're talking about a nodal covariate that's measured on the first mode of a bipartite network. Homophily, unlike these main effects, is totally different than for unimodal networks. So if you watched Brian's video and he talked about homophily, homophily was a very simple thing to model in a in a unimodal network. And I'll just give a quick example here. In the ERGM package, there's a data set called Faux Mesa High, and we're simply going to fit a model that includes a node match term for Faux Mesa High. Node match counts the number of edges on which both of the nodes match on whatever attribute we're interested in. So in this case, we're interested in matching on grade, and we have specified that diff equals true, which means we're interested in differential homophily, which means that each of the separate levels of the grade factor gets its own term in the ERGM. Again, nothing complicated about this. It does not destroy dyadic independence of the model, and so this is easily fit using logistic regression. On the other hand, when we're talking about an affiliation network, there is no longer any sense to the node match term, because we can't talk about an edge whose endpoints match, because each edge has one endpoint from one mode and another endpoint from another. And often these two modes of nodes are entirely different entities. And so matching on an attribute simply is a sensical construct. And that means that homophily for affiliation networks can be a complicated concept indeed. One way of trying to capture a homophily-like statistic is to count the number of two paths whose end nodes match on some attribute. What you see depicted here is a simple network that's got 7 nodes, and the red are only connected to the green. That's the bipartite structure of this network. You'll notice that among the red nodes, there are 3 that have solid boundaries and 2 that have dashed boundaries. That will be our categorical attribute. So we could count in this network how many two paths end with matching red nodes. And you can test yourself on this. There are 4 of them, right? You can see if you can count all 4 of them. And so that statistic, the number of matching endpoint two paths, is one way that we could try to capture homophily. But that is no longer a dyad independent statistic. And that means that using this concept to talk about homophily for affiliation networks suddenly leads to complications that did not exist in the unimodal context. You might also think about different ways of trying to capture homophily. Perhaps we could just look at all of the node pairs that are connected via some two path that happen to match about all of the two paths. Let's just look to see whether two nodes are connected by any two path and that they match. Another way of thinking about homophily is to look at all of the edges in the network and see how many of them are contained in some two path that involves matching edges. These terms, these concepts rather, are implemented. They're all implemented by a couple of terms in the ERGM package called B1 node match and B2 node match. The B1 and B2 refer to whether we're talking about the first mode or the second mode of the network, of the bipartite network. And so what we can see here illustrated, first of all, B1 node match on grade, diff equals true. So now we're talking about we want a separate measure of homophily for each of the levels of grade. And you can see that we get one for 7, 8, 9, 10, 11, 12, and 13. I forgot that there was a 13th grade in this particular data set. On the other hand, we might look at a different measure of homophily. The alpha equals 0 is something I'm not going to elaborate on. This is actually a research level question right now in statistics. We're trying to determine how best to use these ideas to model ERGMs, using ERGMs. And the alpha equals 0 actually corresponds to the first concept here, the matching node pairs concept. There's yet another concept here, this beta equals 0. The beta equals 0 corresponds to this edge count notion of homophily. And these B1 node match and B2 node match terms implement and generalize the ideas on this slide. Turns out that it can be very difficult to fit these ergms. And in fact, the only one of the three concepts from the previous slide that I was able to fit to a simple model for this school network is the one that counts the edges that belong to a two-path that ends in matching nodes. And that uses the beta equals 0 concept. I couldn't get either of the others to fit. And that's because we no longer have dyadic independence. And so homophily for affiliation networks can lead to some problems. Part of the problem here is the size of the network. With 1,262 students and almost 100 clubs, this network is already pretty big, and the computations to do the approximations for the likelihood calculations can be complicated. It's important to realize that not all bipartite networks are in fact affiliation networks. And I have some colleagues from the network modeling group at the University of Washington who are working in bipartite networks that give an example of this, where the nodes are people. They're all people, and the bipartite nature of the networks that they study comes from the fact that they're modeling heterosexual relationships. They're trying to understand how these particular relationship networks might evolve. We're not going to talk about time evolving networks in this talk. We are simply going to use their ideas to simulate a cross-sectional network. And this particular network of 200 hypothetical individuals is simulated so as to match the demographics of Seattle based on the National Survey of Family Growth, the NSFG. And this team that's based at the University of Washington is using this NSFG to study these networks based on egocentric data. So the simulated network that I'm talking about here has 200 vertices. It's got 65 edges, and we're going to see what it looks like here on this next slide. So once again, generated randomly. The function that was used to generate it in the ERGM package is called SAN. That's simulated annealing. And simulated annealing is used in this case to try to find a randomly generated network whose statistics, as measured by whatever we think are important, match a particular set of statistics. And so the SAN in this case was fed some target statistics, and then we told it to go off and generate a network that matched those statistics as closely as possible. And once again, those statistics were based on demographics of Seattle, scaled down to a hypothetical population of 200 individuals. And this, again, is a bipartite network. All the nodes are people. And there are actually 3 different types shown in this plot. And this is according to, well, let's see, the red nodes are male. And then we have two separate categories of males who have sex with females and males who have sex with either females or males. And even though that third category exists here, we are only interested in the existing relationships between males and females. Again, that makes it a bipartite network. And because it's bipartite where all of the nodes are homogeneous, i.e. they're human beings, we can now do things like use node match to talk about homophily in this network. For instance, you might be interested in homophily due to race or due to age. And in this particular context, those concepts are meaningful and they don't destroy the dyadic independence of an ERGM that one might want to fit. So the bipartite nature of the network that I just showed you can be thought of as a sample space constraint. In other words, there are simply some potential relationships that are disallowed from the sample space of allowable networks. And in this case, we're going to disallow any relationship between a female and a female or between a male and a male. And so we place these constraints on the sample space of all allowable networks. In addition to that, there is one more constraint that I will talk, that I will talk about here. And it's the BD constraint. And because my colleagues are interested in modeling relationships that are not concurrent with any other relationships, in other words, these are monogamous relationships, they also want to place a constraint on the number of allowable relationships that an individual can have. It is simply not allowed to have a degree of 2 or greater in this particular network. And because the constraint on no female-female nor male-male relationships is in place, and because the constraint on the degree not being allowed to be 2 or greater are in place, this sample space suddenly becomes quite complicated. And even a simplistic ERGM in normal settings, like an ERGM that contains only the edges and a node match.race term, can be complicated in the context of these particular constraints. So this fit that you're looking at, these coefficient estimates were obtained not using logistic regression, but using a simulation-based approach that's a lot more complicated than that. And it's because these constraints are in place. Here's a separate way within the ERGM package to model these constraints. You can place what's called offset terms into the model. And in this case, what we're going to do is we're going to put an offset of concurrent. Concurrent is a statistic in an ERGM that counts the total number of nodes that have degree 2 or greater. And node match sex counts the number of matching on sex pairs, that's edges that are connected by nodes that match on sex. And what we're going to do is we're going to throw those terms into the model, and then we're going to attach coefficients to them of negative infinity. And an offset term is defined as a term in an ERGM that has a fixed and known coefficient. And because these terms are going to be given fixed and known values of negative infinity, it means that you will never see any of these kinds of terms. So the term values always have to be 0. So you will never see concurrent relationships, and you will never see relationships that match on sex when you throw these offset terms into this particular model. And you can see that when we fit an ERGM with these offset terms in it, you get estimates, you get estimates, which I will show you here. Well, that was more complicated. The estimate for edges and the estimate for node match.race. And you'll see that those estimates are about the same as the estimates that we got on the previous slide. The reason that they're different is, once again, there's a stochastic element to this fitting algorithm. Because we can't use logistic regression and get an exact answer now, we have to use a random MCMC-based procedure. And so these two answers are essentially the same, and yet they're a little bit different due to the randomness. So the sample space could be simply bipartite if we removed the prohibition on concurrent ties. And simply wanted to make the point here, even though this is a little bit outside the scope of our ERGMs with bipartite ERGM presentation, that if you have a constraint that exists in your particular network, but you don't model it, then the estimates will be biased. So in particular, if my colleagues at the University of Washington were interested in modeling monogamous relationships, but they failed to place that constraint on the sample space, even though they may have only observed a network that has only monogamous relationships, during the fitting process, you're going to visit the entire sample space, and that's going to bias your estimates if you don't explicitly put that constraint in there. So the rest of this slide is simply an illustration of what could happen if you removed the concurrency constraint. Now everything is actually quite easy, and this edges node match race model is easy to fit. You can do it using logistic regression. And in fact, I'll leave you with this homework question. You can take a look at these two coefficient estimates, and then down here, I claim that you can use the information provided by these statistics and generate these two coefficient estimates by hand. So again, that's your homework. Thank you very much for your time. I also want to thank, in particular, Jim Moody and Brian Aronson. We've referred at various points in this presentation to the videos recorded by both Jim and Brian, and the links that are shown here are the links to their videos.